I mean, I think we are really delighted to have you. I think you're a very well-known figure, both on the research, and I know you're involved in commercialization of some perovskites, and you'll be telling us about this key theme of stability, as far as I understood. So, looking forward to your talk.
Thank you. Thank you for this opportunity to present some of the work my team has been doing. First of all, I'll say a bit about a consortium that was recently created with funding from the Department of Energy, and we're working on perovskite silicon tandems, and this tells you up front which structure I think can be the most stable. And in this consortium, we're both looking at monolithic tandems like the ones you see on the left, as well as mechanically stacked tandems like you see on the right. And this is a consortium with academics, NREL, and several companies, including Swift Solar, Beyond Silicon, and Tandem PV. As we've already seen in a couple of talks, there are different approaches to commercializing perovskites. And briefly, you've got the single junction approach, and some believe that you should just aim for really low cost. And then there's the perovskite silicon tandems. And then there's the all thin film tandems where you don't need any silicon. And right now, triple junctions are not as efficient as even a single junction, but I think we're going to see a lot of activity in that space. And I like to think a lot about what is going to determine the winner, which of these approaches is going to be the best. And the heavily studied ones are efficiency, cost, and stability under light and heat. But I think it's quite possible that some less studied X factors are going to determine the winner. Things like problems with scribe lines, or what happens in reverse bias to a partially shaded cell, or possibly mechanical durability. And I think a great approach for obtaining superb stability is to use a combination of atomic layer deposition and sputtering to have an electrode that is highly impermeable. So it's both a functional part of the device and a barrier. And not only is it keeping air out, but it is keeping stuff in. And if you make iodine gas, for example, the barrier can hold it in. Originally, my group collaborated with Axel Palmstrom and Stacy Bent to build this. And we were really doing it just to have a transparent electrode in tandem so that we could get the light in. But right away, we noticed a 4 order of magnitude improvement in stability. And a lot of that is the barrier properties. Some of it is that halogens are less reactive with these TCOs than they are with metals. So I really liked that approach, which is why I have concerns with the module design that a lot of people are using, at least for single junction cells. If you've made this really nice barrier film, in my opinion, the last thing you want to do is scribe, right through it. Not only are you losing your barrier, but if you're using laser ablation, then you're likely to have thermal damage on the sidewalls, and you could have some lead iodide. Lead iodide acts as a photocatalyst, so not only do you have damage at the edge, but the damage is going to propagate away from the scribe lines over time. And I hear people talk about repairing the damage, but there's a lot of scribe line area in a module, and I'd be concerned about getting all of that damage repaired and not having any scribe regions that have any problems. So I just want to point out that in a perovskite silicon tandem, you don't need to do any scribing. You can cover the entire wafer with the tin oxide and the ITO. No need to penetrate that, and you can just take